So, in the previous lecture, we deduced several interesting properties of Bessel functions. So, please remember that the Bessel functions, uh, we found series solutions and of the Bessel equation, and those series were fairly complicated series. So, in spite of that, the fact that we could say so much about these Bessel functions, their properties, their zeros, etc., etc. So it was really remarkable. At least I found that very remarkable, and I hope you people liked it also. So today we will continue the with the same theme as in the previous lecture. So the results that we will see today will be of the same kind that we saw last time. So let's just recall one by one these results and the order in which we proved them. So that will give us some uh, a better idea of the picture. That will clarify the picture in our mind. So we first proved that between any two consecutive positive zeros of jpx, there is exactly 1 0 of jp minus 1x and exactly 1 0 of jp plus 1x. Okay. And using the Bessel identities, we saw that the Bessel functions j m plus half x, where m is an integer, are elementary functions. I had left it as an exercise to all of you to convince yourself using induction on M that this is true. Right. And I hope you did that exercise. So it's not a difficult exercise, and you just had to use the Bessel identities. Uh, okay. So we stated without proof the mysterious theorem of Liouville, which states the following: the only values of p for which jpx is an elementary function are p belongs to z plus half. So indeed, I would imagine that it's even hard to guess such a statement. I mean, how would you even guess? Suppose someone were to ask you, okay, we have written these jpx's, and for each p in the real numbers, we have a jpx. For p in real numbers, we have this function. We have the series jpx, which is a series on 0 infinity, and the series is not a particularly nice looking series. The coefficients are quite complicated, and it's quite amazing that one is even like bold enough to make such a guess, that could this be true. Okay, so let me just erase this. So it's really a fantastic result, I would say. Yeah, I don't know anything about the proof or how hard or how easy it is, etc., etc., but I know that this theorem exists and it was proved by Liouville. So this sort of ended one part of our discussion in the previous lecture. After this, we went on to analyze the zeros of the Bessel functions. Uh, so this analysis used only the form of the differential equation, and hence is quite remarkable. And hence this analysis is quite remarkable. So let's just recall the main results that we proved. So one of the theorems results that we proved, and each of these results, some of them were tricky, but all of them, they were not very difficult. Uh, so the first result we proved was term separation theorem. We proved and used. So consider the differential equation y double prime plus p of x y prime plus q of x y equal to 0, where p of x and q of x are continuous on some interval a comma b. And if y1x and y2x are two linearly independent solutions, then uh, y1x and y2x have no common zeros in the interval a comma b, and between any two successive zeros of y1x, there is a zero of y2x and vice versa. Okay, so obviously we can apply this theorem to our Bessel equation, to the Bessel equation. So we have, when we write our Bessel equation like this, so Okay, so let me just verify that this is correct. Right, this is okay. Sorry about this. Okay, so right. So when we write it in the standard form, this becomes y double prime plus 1 upon x y prime plus x square minus b square by x square y equals 0. Right. So both these functions, they are continuous on the interval 0 infinity, and that's really where the region where we are interested in. That's the region where we are looking at the solutions. So this theorem applies, and it tells us something about the two independent roots, jp and j minus px, right? So yeah, so if p, uh, yeah, I don't, yeah, if p is not an integer, then uh, we had that jpx and j minus px are the two linearly independent solutions, right? I don't. This much is definitely true, but maybe we need that p is. I don't know. Does anyone remember? If anyone remembers, can they type it into chat? Do we need p to be not in integers, or not in 0 minus 1 minus, or not in 0 1 2 etc etc? Okay, anyway, I don't remember right now, but let's just go ahead. So this tells us something about the zeros of the Bessel equation. Then for further analysis, we converted our equation y double prime plus p of x y prime plus q of x y equal to 0 into normal form. So this is the normal form, u double prime plus q of x is equal to 0. And this, if we take a solution y of this first differential equation, then uh, that is related to the a solution u of the second differential equation by this equation, y of x is equal to u of x times v of x. And v of x never vanishes, so the zeros of y of x are exactly the same as zeros of u of x. And our aim was to analyze the zeros of y of x, and so therefore it's sufficient to analyze the zeros of u of x. So we want to know what are the zeros of y of x, where they are, etc etc. So it's sufficient to understand the zeros of u of x. So some of the results we proved last time were that if u double prime plus q of x is equal to 0, this is our differential equation, and q of x is continuous on this interval alpha beta, and if we take any finite interval a comma b inside this open interval alpha beta, then u of x has only finitely many zeros in a comma b. So that's one result we proved. This was the proof of this was quite easy. Okay. The other more interesting result we proved was if q of x is positive for some sufficiently large x, and when we integrate from x naught to infinity, the integral is infinity, then u of x has infinitely many zeros on, well, 0 comma infinity or x naught comma infinity. And we use these two results to say something about the zeros of the Bessel functions. So the above two results were applied to the Bessel equation, and after we convert the Bessel equation to normal form, it looks like this: u double prime plus, so this is our q of x, okay, I've written it below, u double prime plus this whole function 1 plus 1 minus 4p square by 4x square. This whole function into u is equal to 0. So let us first consider the case p strictly less than half. So from now on, let's just focus on this case. Focus on this case. P strictly less than half. So in this case, it is clear that we have q of x is 1 plus 1 minus 4p square. This quantity is positive, and x is of course positive. So this quantity is going to be positive. And therefore, this q of x is strictly greater than 1. Okay. Thus, 8 tells us that JPX has infinitely many zeros on 0, comma infinity. So point 8, remember, was this thing. So you can easily check that when we integrate q of x, and let's say taking x naught to infinity, then we will get infinity because, yeah, I suppose because we will have a 1 upon x here. Is that what I want to say? Mm. Oh, no, because, yeah, because we have this constant function 1 over here. And this, yeah. So, of course, sorry. So, q of x is strictly greater than 1. So, yeah, when we integrate from x naught to infinity, we will obviously get the area under the graph will be infinite. And therefore, 8 applies. Right? So, that will tell us that JPX, it has infinitely many zeros on this interval, on 0 infinity. Okay. And 7 tells us that these zeros tend to infinity, as any finite interval AB will contain only finitely many zeros of JPX. So these zeros, they cannot accumulate anywhere on the real line. Okay. So this is already quite interesting. Yeah. Now after this, we said let ZP denote the zeros of JPX. So yeah, so this is the picture. So this is our interval 0 to infinity, and I just take the first zero, first positive 0, x1, then the next one, x2, x3, and so on. And the question was, what can we say about these zeros? Can we say something about them? Right? So we proved that these lengths, sorry, these lengths, they are increasing. Right? These lengths, they are increasing. That's what we proved last time. And one of the tools we used was the Sturm separation theorem. I'm not, yeah, I think we used, I'm sorry, not Sturm separation theorem, okay, I don't remember right now how we proved this. I think we used the Sturm comparison theorem, which is a very interesting theorem. So we proved that the difference xn plus 1 minus xn is a strictly increasing sequence. So this is what we proved. And what I'm confused about right now is whether we used the Sturm comparison in this or whether we did not, or if we did not. So, but let me state the Sturm comparison theorem in any case, which is we will use it now. But yeah, I'm a bit confused as to whether we used it in proving 10 or not. So it says the following. So let me just highlight this. So once again, it's a very interesting theorem. Let y of x be a non-trivial solution of this differential equation. Y double prime plus q of x is x times y is 0. Let z of x be a non-trivial solution of z double prime plus r of x times z is equal to 0. And if this q of x is strictly greater than r of x, which is strictly greater than 0, then y of x vanishes at least once between any two consecutive roots of z of x. So yeah, So this sort of ends the discussion of what we did last time. And the last thing we proved was that we proved this point 10, this one, that this sequence is strictly increasing. So today what we are going to do is, today we begin by trying to show that the sequence xn plus 1 minus xn, it tends to pi as n tends to infinity. Okay. So, okay, are there any questions till now? Let me just pause for a few seconds. Okay, if there are no questions, let me go ahead. So some of these slides will be repetitive from. So let Zp be the zeros of the Bessel function Jpx on 0 infinity. Since Zp is an infinite set, it is not bounded. This is what we observed above also. So we will consider the following question. Write Zp is equal to x1, x2 dot, dot, as an increasing sequence. And what is the limit of xn plus 1 minus xn as n tends to infinity? So we will need this term comparison theorem. So this term, I'm just writing it once again. Okay. And this is, okay. In this slide, we have reduced the Bessel equation to standard form. So let's just focus on this case right now for today's lecture. Yeah, because the other cases are identical. So if we understand this case, then we understand understand how to do the other case also. Okay. Right. Right. So let's look at this case. So in this case, so here q of x is strictly greater than 1. So we can look, and 1 is strictly greater than 0. So we can look at this equation, right? So this is one equation. So yeah, this is u double prime. This is one equation. And the second equation is, let me say z double prime. Oops, sorry. Let me take z double prime plus z, the constant function 1, is equal to 0. So I can take any root of this, and every root of this is going to look like alpha cos x plus beta sin x, where alpha and beta are real numbers, right? And now we take this solution y of x of this. And what does terms comparison theorem say? It says that, oh, I'm sorry, where is the theorem? It says that y of x vanishes at least once between any two consecutive roots of 0, right? So it says that this function y of x vanishes at least once between any two roots of this. So if we make we can choose our alpha and beta. Yeah, okay. We can choose our alpha and beta in such a way. So given any real number, let's me take a real number x naught. We can choose an alpha and beta such that the zeros of this function are exactly x naught plus pi, and so on. X naught plus 2 pi, and so on, right? So this is, yeah, so this is saying that, uh, let me go to the next slide. If p is strictly less than half, between any two roots of this thing, there is a root of ypx. Right. Okay. Yeah. So it's, yeah. So basically, it's saying that let me take the real line. Well, I should. I mean, yp is, we are only considering the positive. Right. So let me just take any x naught, and let's just look at x naught plus pi, x naught plus 2 pi, x naught plus 3 pi, and so on. Right. So there's always a root of JPX somewhere here. So it's a very interesting result. Okay, so let's go to the next slide so we can say more than the above. So in this, so this is a proof of the fact that this is something which we did last time, so I don't want to repeat this. So this is a proof of this fact that the difference of the roots is increasing. So that's what we have proved here. That, yeah. So here we took A strictly less than B strictly less than C are successive roots of JPX. Right. So this is A. Oops, sorry. There's A, there's B, and there's C. And here we have proved that this difference, this length, is strictly greater than this length. That's the proof here. This is something which we had done last time, so I don't want to go over it again. Right. Oh, here we are. And so we do use Sturm's comparison theorem. Okay. Okay. So we have proved, yeah. So, okay. So let's see. Next, we claim that the difference between any two successive roots of u is strictly less than pi. All right. Yes, that sort of follows very easily. So if not, okay, yeah. If not, then let a strictly less than b be successive roots such that b minus a is greater than or equal to pi. So we have these roots. So let me just explain what we are doing once again. I mean, it's, yeah. So we are in the situation p is strictly less than half, right? And let's say this is a 0. And we are claiming that, okay, so let's take any two successive roots, this a and this b, right? And we are claiming that b minus a is strictly less than pi. That is our claim. That's what we want to prove. Okay, so let's see how to prove this. So since u has infinitely many roots, this is something which we have seen, and the difference is strictly increasing, we may assume that b minus a is strictly greater than pi, right? Because, so yeah, I hope it's obvious what we are doing, because here we have our interval, here we have 0, and here we have a, here we have b, and we know that there are infinitely many roots, so there's another c, and we have just proved that this distance is strictly, this length is strictly greater than this length, right? So if b, so instead of taking a and b, we can just take c and b, and we can assume that we have taken two successive roots such that their difference is strictly greater than pi. Okay, so what do we do next? Well, Wakar is, I'm pretty sure that we had proved that the difference of roots is strictly increasing, because I had done up till this slide, I think. Yeah. Okay. So let's go on. But now we can choose alpha and beta real numbers such that alpha cos x plus beta sin x has two roots in alpha comma beta in I'm sorry, a comma b, which contradicts Sturm's comparison theorem. So let's see what is happening here. So here we have, so this is, once again, this is 0, this is a, this is b. So this length we are assuming is strictly greater than pi, right? So I can choose something very close to a. So let me say a naught, and such that a naught plus pi is here, right? And now I can choose my alpha and beta such that uh, alpha cos x plus beta sine x has successive roots at a naught and a naught plus pi, right? But now let's, and we know that y of x, a and b were successive roots of y of x, so therefore there is no root over here, right? But this contradicts terms comparison theorem. So let me just go back to that slide, right? Here we had proved that, and I had explained once again today, between any two roots of this thing, there is a root of jpx. Okay. Uh, so that proves this claim that the difference between any two successive roots of u is strictly less than pi. So we now have to, so all these, yeah, right. Thus we have proved that if xn are the roots of u in increasing order, then the difference xn plus 1 minus xn is strictly increasing and bounded above by pi. Right. So next let us show that these differences, they actually converge to pi. I mean, so they are like, so if, yeah, so these differences, they will, so there's pi and these differences, they will tend to pi. Okay. So let's assume that this is not the case. So this is a increasing sequence of numbers. Sorry. Right. So this is an increasing sequence of numbers and they are bounded above by pi, right? So I'm looking at xn plus 1 minus xn. So one of them will be here, then they are increasing. So, and they are bounded above. So let's say the supremum is some gamma and gamma is strictly less than pi. So then I can choose a delta which is positive, I'm sorry, which is strictly greater than 1, such that this gamma, well, okay, yeah, such that this pi by delta is a little bit smaller than pi, but it's greater than gamma. Okay, so let's take a delta like this. Okay, so Nikhilesh has asked a question, why not A strictly greater than A naught and B strictly less than A naught plus 2 pi? So, okay, so I don't understand your question. No, the point is we want to get a contradiction, right? So let me just go back. So our aim is to get a contradiction. We want to prove that if there are zeros a and b, such that if there are successive zeros a and b such that b minus a is strictly greater than pi, then we want to get a contradiction, because our aim is to prove that we take any two zeros of the Bessel function of, or this function u whose zeros are same, then their difference is strictly less than pi. Right? So we assume that the difference is greater than or equal to pi, and since we know that there are infinitely many roots and their difference is strictly increasing, we can reduce to this case, and now we want to get a contradiction. So I don't know, to get a contradiction, we are using this we are using Sturm's comparison theorem. So this distance between a and b is strictly greater than pi, so I can choose a naught which is very close to a, and then my a naught plus pi is going to be strictly less than b. And now I can choose my functions alpha, and I can choose real numbers alpha and beta, such that alpha cos x plus beta sin x, this has successive roots at a naught and a naught plus pi. And Sturm's comparison theorem is going to tell me that okay, this function jpx, it has a root somewhere in between two successive roots of alpha cos x plus beta sin x. But that's a contradiction, because this function did not have jpx did not have any root between a and b. So is it clear? Yeah, I mean, so our aim is to get a contradiction. So, and what we are trying to prove is that if this thing happens, if such a thing happens, then that will contradict Sturm's comparison theorem. So therefore such a thing cannot happen. That's how we proved it. Okay, thank you for your question. So once again, we approved this. And now, yeah, we are doing this. So we want to show that the difference converges to pi. So if not, it converges to some gamma, which is strictly less than pi. And then we can find a delta which is strictly greater than 1, such that delta is going to be very close to 1, but it's going to be strictly greater than 1, such that pi divided by delta is going to be smaller than pi, but it's larger than gamma. Okay, great. So what do we do? So the function q of x, so remember what was q of x? Uh, so q of x was equal to 1 plus 1 minus 4p square plus 4x square. This is strictly greater than 1 because we are focusing only on the case p strictly less than half. But notice that as x tends to infinity, uh, right? So this is my graph. There's 1. So my q of x is going to be something like this, right? It's going to tend to 1. So my delta square is somewhere over here, right? So there will be some x naught sufficiently large such that q of x naught is strictly less than delta square. So once again, we apply Sturm's comparison theorem on the interval x naught to infinity to the differential equation this to this differential equation u double prime plus q of x equal to 0 and z double prime plus delta square z is equal to 0, right? So when we apply Sturm's comparison theorem, so what does it say? So let's write down the two differential equations. Delta square z is equal to 0, and the other one is u double prime plus q of x u is equal to 0, right? So here delta is strictly greater than q of x is strictly greater than 0. So what we will get is that between any two roots of between any two roots of u of x, there is a root of z of x, where z of x is a root of this equation. Right? But now once again, we are going to get a contradiction. So how are we going to do it? Okay, I've already explained this. Thus, between any two roots of u of x, there is a root of z of x. Okay? So let a and b be two consecutive roots of u such that, okay, yeah. So we know that, once again, we know that there are infinitely many roots. So, and our x naught is somewhere over here. So x naught is chosen such that this happens. And then the roots is strictly increasing. So we have our a over here and our b over here. So this difference is strictly less than gamma because the difference of the roots was increasing to gamma, right? So this is my gamma, this pi by delta, and this pi. So the difference of the roots is strictly, so this b minus a is strictly less than gamma, which is strictly less than pi by delta. Okay, so I hope the setup is clear so far. So once again, we find a prime and b prime such that this happens. X naught is strictly less than a prime, which is, so a prime is somewhere over here. So a prime is somewhere over here. And a prime plus pi by delta. This is b a prime plus pi by delta. Right? So what we want is, we will choose a prime very close to a. Now this distance is strictly less than gamma, which is strictly less than pi by delta. So this a prime plus pi by delta is going to be a little bit ahead of b. Okay. So this distance between a prime and this, oh yeah, I mean by definition this is a prime plus, this point is a prime plus pi by delta. So maybe I can try to make it in a different color. So this point is a prime and this point is a prime plus pi by delta. Okay, and now we once again, yeah, oops, right, sorry. So what we do is, I'll go back to that slide again. So once we have that picture, then we will look at the solutions to this differential equation, z prime plus delta square z is equal to 0 are exactly of this type. Alpha cos delta x plus beta sin delta x. right? So we will choose, so let's just look at delta is fixed, so we will choose alpha and beta such that this function alpha cos, this function alpha cos delta x plus beta sine delta x, this has a root at a prime, right? Then its next successive root is going to be at a prime plus pi by delta at this point. Okay, but so what did we, so that is a that we are taking that to be z, we are this is our z of x, right? But what did we had concluded that between any two roots, between any two roots of u of x, there is a root of z of x, right? But now with this choice of z of x, a and b are roots of u of x, but there is no root of z of x in between these two. If a prime is here, then a prime plus pi by delta is beyond b, right? So once again, that's a contradiction. So yeah, I hope that is clear. Right. So if you have any questions, you can ask me now. But we have proved a very nice and a very beautiful theorem, which a priori looked, I don't know, there's no way of proving such a fantastic result by just looking at the series of JPX, which was like a horrible and complicated series. So similarly, we can prove that if P is strictly greater than half, then the sequence of difference of roots of U is decreasing and it tends to pi. So we just repeat the same analysis by changing the sign, by changing the, yeah, greater than to less than or something. I'll leave that as an exercise. So we will pause over here, and if people have any questions, they can ask me. So maybe I can go to the previous slide and pause over here. So if there are no questions, then let's go ahead. So yeah, so I suppose that this ends like a very nice and somewhat theoretical, if I may use that word, part of our course. So I personally found these results very fascinating and interesting, and the ideas behind them. So I hope you also enjoyed it. Okay, so let's go ahead. So these are some, I don't know, graphs of Bessel functions, but that's not so important. So let's go ahead. Why are we concerned with the zeros of Bessel function? Okay, I'm going to skip this slide. Now, the next theme that we are going to come to is expansion in terms of Bessel functions. So remember that I had written this as a theme which we will repeatedly visit in our course. So what do we have? We have a certain normed linear space, right? Normed vector space is the term I had used. So yeah, I suppose here it's going to be L201, but we will just find out. And so a collection, so a collection of solutions to a family of differential equations gave rise to a normed basis for this norm linear space. So in this case, this norm linear space is L201. But here we will, well, okay. So I should, okay, I should be careful. I should not say L201 because we will just see. Let's go ahead. So yeah, but this is the theme. So once again, we will have a normed vector space. So let me remove L201 because we are not talking about L201. There's a different norm. That means your norm linear space V, norm vector space V. Okay, this is what we had seen. I mean, I had mentioned this statement at the end of our discussion on the Legendre equation. Okay, so for a scalar A, the scaled Bessel functions JPAX are solutions of this differential equation. So this is an easy check. So you can convince yourself that this is true. So yeah, so here what is the function is x goes to JP of AX. So this function, it satisfies this differential equation. This is called the scaled Bessel equation. So simplest and most useful expansions are of the form f of x is equal to. So given any function f, we want to write it in this form. Right. So yeah, so here we are fixing our p, and lambda p n's are the zeros of this Bessel function jpx. Okay, we're fixing a p greater than or equal to 0, right? So we have this 0, this lambda p1, lambda p2, lambda p3. We just saw several properties of this is very interesting. Okay, so we just saw several properties of this these roots. The difference between, there are infinitely many of them, and the difference between them is an increasing sequence, and that difference is tending to pi, right? So we can look at these various functions, jp lambda p1, jp x, jp lambda p2 x, and so on. So this is a family of differential equations where this a p is fixed and our a is varying in this set of zeros, right? So for each of these differential equations, we pick up this function, and these functions, they give us a norm basis of for a certain norm linear space, right? Which is exactly precisely the meaning of this equation, right? So I will just make this precise in the next slide. So how to compute coefficient before that? Okay, before that. So we are looking at the space of functions on 0, 1, on this interval 0, 1, and we define an inner product f comma g as integral 0 to 1 x times fx times g of x dx. Okay, so this is different from, so the inner product, so let me just write it down. The inner product in L201, that's why I removed that later on, is f comma g is equal to integral 0 to 1 f of x dx. There is no x over there, dx. Okay, so the space, the vector space of functions is the same, but the inner product we define is different. Okay, so I hope that is clear. So on the same vector space, we can define various different inner products, and each of those is going to give us, different of them may give us different inner product spaces. Okay, so this is similar to the previous inner product, except that f of x, okay, there is no previous inner product. This, well, I just want to emphasize that, yeah. I suppose by, I don't know what I mean by previous inner product. Maybe I meant in the Legendre case. Okay, so here we are integrating from 0 to 1, and we are multiplying it with x also. So we call a function on 0, 1 square integrable with respect to this inner product if, so the definition of square integrable is always f comma f is strictly less than infinity. And f comma f, in this case, this condition translates exactly into this. So the multiplying factor x is called a weight function. Okay, this sentence is not at all important, but okay, it's just giving some name, but we don't care about this. Okay. So now, yeah, so now we have our norm linear space V. Okay, so V is this vector space. Let me loosely write vector space of functions on 0 1, yeah, with inner product f comma g is equal to integral 0 to 1 x f of x g of x. So we are looking at this vector space, and now we want to, so here is a theorem. The set of scaled Bessel functions, this form an orthogonal family with respect to the above inner product. That is, this inner product jp. So here the p is fixed, and this lambda p1, lambda p2, etc. This, as I said before, these are the roots of jp. So we have our function like this. This 0. So we fix p once and for all. So this lambda p1 is lambda p2, and so on. And then we look at these scaled Bessel functions. And well, so first of all, they form an orthogonal family. Means when I integrate two of these, I get 0 if k is not equal to L. And if k is equal to L, well, then I'll get some norm. And we need to show that this norm is equal to this thing, has this value. I will get some positive number because we are integrating a function which is positive if k is equal to L. I mean, it's just going to be the square of this jp whatever, right? So that's a positive function because x is also positive. And that quantity we have to show is equal to this thing, this half of this stuff. Okay, and then plus it's a theorem that, I mean, that's probably going to be some hard theorem, that every function we can write it as every function f such that f comma f is strictly less than infinity, and this is equal to integral 0 to 1 x f of x square dx. This finite. This can be written, f of x can be written as a series of this thing, right? That's what we are going to prove. But first, what we are going to do is we are going to prove the orthogonality. So let's see that. Proof of orthogonality of scaled Bessel function. So this is very simple. So let's just take a and b to be positive scalars. And we, for convenience of notation, we say u of x is jpax and v of x is jppx. Then u of x satisfies this equation. This is the simple check which I had stated earlier. And v of x satisfies this equation. Okay, so let's go ahead. So we multiply this one with v and multiply this one with u. Right? And when we subtract, we get this equation. Okay. This will be some easy check. So you just believe it from now. Or right, it's even obvious too. If we just stare at it for a few seconds, it's obvious. So let's go to the next one. So this equation we rewrite like this. Okay, which is rewritten like this. Right. Okay, so these steps are fairly clear and obvious. You just have to stare at it and think for a few seconds. All right. So now we integrate both sides, right? We just integrate from 0 to 1, I suppose. 0 to 1. So let's see. So right on this, so I have written this on the right on the next slide. So we have this thing. This is equal to integral. Yeah. So that's, we had a derivative. So we just have to evaluate this function from 0 to 1. So if you look at this, we have a derivative here. So we just have to look at, yeah. So this function has to be evaluated at 0 and 1. When we evaluate it at 0, because there is an x over here, that value is 0. So only this much remains. Okay. So let's go to the next slide. So u remember is jpax and v is jppx. So, and this thing evaluated at 1 is, yeah, we just put x equal to 1. So it's j prime pa jpb minus j prime pb times jpax. Okay. So now we are going to put a equal to lambda pk, right? And b equal to lambda pl. So let's say a and b are distinct. That means this is not equal to 0. This is not equal to 0, right? Now b is a root of jp, right? So jp b, so this term is 0. And similarly, a is a root of jp, so therefore this term is 0, which implies that if a is not equal to b, so if we have lambda pk and lambda pl, right, and k not equal to l, so we have proved that this integral is 0, which is exactly what we wanted to prove, right? We had this inner product and we have this jp lambda pkx. We had this scale function, Bessel function, jp lambda pl x, and we wanted to prove that this inner product is 0 when k is not equal to l. Okay, so that's great. So let's go to the next slide. Next, we want to compute the norm of jp lambda pkx. So what do we do for that? So uh, we multiply this differential equation with 2x square u prime. Okay, and we write it like this. We write it in this form. Okay. Okay, it should be an easy check that uh, this object over here, that can be written as this object over here. All right. So I leave that check to you. It should be a completely trivial check, but let's just assume that for now and go ahead. And then we integrate on both sides. So what do we have here? Okay. Okay, I'm sorry. So yeah. All right. So let me just erase this for the time being. I'm sorry. So we have this is equal to 0, which means that these two are equal, right? And now we are integrating both sides from 0 to 1. So what happens? So over here, when we integrate this from 0 to 1, we get the term on the right in the next slide, which is this term, right? And this term on the left that appears with a derivative. So we just have to evaluate this function at 0 and 1. So let's see what happens when we evaluate it at 0 and 1. So since p is greater than equal to 0, yeah. So remember that jpx, right? This was some series of the type some summation. There is some coefficients and x to the power 2n plus p. So n was greater than equal to 0 here. Okay. So since p is greater than equal to 0, so if p is equal to 0, then this p times u will just vanish. And if p is strictly greater than 0, then this jp, if p is strictly greater than 0, then jp of 0 is 0. Because p is going to be strictly greater than 0. And this, yeah. So the series is going to look like x to the power p times some series, x to the power 2n star, some coefficients, right? Okay. So therefore, right. So therefore, this term is going to vanish at 0, and these other terms are also going to vanish. So therefore, we only get this one. Yeah, so that's what I've written. This whole thing at 0 is 0. Okay, so let's look at the other. So what have I written? U prime 1 is equal to a jp prime a. Okay, so u is equal to jpax. Right, okay. So this is true. That is obvious. And therefore, we get that the evaluation of this function at 1 is going to be equal to, yeah, I'm putting x equal to 1. Right, okay. Right, so if you stare at it for a few seconds, you'll easily convince yourself that this function evaluated at 1 is going to give us this. And we put a equal to lambda pk to get that, to get this, yeah. So this, we get that this is equal to this thing. Right, when we put a equal to lambda pk, this vanishes, only this remains. And that's exactly what is written here. Okay. So therefore, integral, right. So therefore, I mean, this gets cancelled with this. So what remains is this integral, this is equal to half of this thing. And this is equal to this thing over here because we have used the this Bessel identity. So inside this Bessel identity, when we put x equal to lambda pk, this term vanishes. So only this one remains. Okay, so let's go ahead. And this is our theorem, which, yeah, this is what I have said many times, that these scale Bessel functions, they form a normed basis for our vector space, for our inner product space. And the coefficients Cn are going to be given by these inner products. So this is the Fourier Bessel series of f of x for parameter p. So this theorems of this type will be very hard to prove. I mean, you would probably need a lot of machinery. But what we have proved is, we have proved that these scale Bessel functions, they are orthogonal to each other, and we have also computed their norm. Okay. And once again, when I say this equality happens, what do I mean by that? It means that when I look at these partial sums, Snx equal to summation n equal to 1 to, let me call this capital N, right? Cn jp lambda p comma nx. I look at this function. So the norm of f minus snx tends to 0. So norm as in the inner product of this function with itself. Yeah, so I hope you know what yeah. Tends to 0 as n tends to infinity. So once again, as we saw in the Legendre case, this is going to tell us convergence in norm. But what can we say about pointwise convergence? So that's going to be the next theorem we are going to get at. Okay, we are going to skip this example. So let me just, yeah. Convergence in norm. So the Fourier Bessel series, yeah. So this is the Fourier Bessel series, converges to 0 as m tends to infinity. That's what I had written earlier. And for pointwise convergence, we have, so assume that this is the standard template of the theorem. F and f prime are nice functions. And then the Bessel series. So on the one hand, we have f of x, and on the other hand, we have the series n greater than equal to 1, Cn jp lambda p comma nx. So this series, it converges to, for if x lies strictly between 0 and 1. So then this, and let's say x is over here. Then the series converges to, I take the limit of f x minus and the limit of x plus from coming from both sides, and then I take the average of those. And at x equal to 1, the series always converges to 0. Okay, wow. Okay, yeah. That's right. Because at x equal to 1, all these numbers are zeros, right? Because we just get jp of at x, when we put x equal to 1, we get jp of lambda p comma n, which is 0 because lambda p comma n is a 0 of the Bessel function. At x equal to 0, if p is strictly greater than 0, then also it converges to 0. Once again, because if p is strictly greater than 0, then jp of lambda, whatever, 0 is 0. Okay. At x equal to 0, if p is equal to 0, then it converges to f0 plus. Okay. So if p is equal to 0, then it converges to the limit of f of x as we tend from this direction. So all such theorems that we will see in this course will come in this standard format. There will always be a inner product space, and there will be a family of differential equations, and using those we will cook up some functions, and these functions will turn out to be orthogonal and also will form a normed linear space, and also will form a normed basis for our inner product space. And finally, we will have some pointwise convergence theorems of this type. So I think this is a good place to stop today's lecture. I will take questions if there are any. All the best for the quiz tomorrow.